So what I'm going to do today is talk about the last section of the course, which is properties, to discuss properties of DTFT, discrete time Fourier transform. Now, there's a section which is Fourier transform for periodic signals that I have skipped in the interest of time, and also because we've not talked about Fourier series. So I considered, I thought uska koi point nahi hai. So I'm going directly to the properties section. The first, so here's the overview of what Fourier transform is, like we discussed last time, right? So Fourier transform, we said the is x of e raised by j omega. So this is the notation we're going to use, and so where this is actually a function of this independent variable, which is omega, right? How could we read the screen linearly? Okay. Right, so the independent variable is this omega, and so x of e raised by j omega as the continuous time Fourier transform in the discrete time indicates what is the contribution of the discrete time exponential of the frequency omega. Okay, and this is how you compute the Fourier transform. And how do you compute the inverse Fourier transform? This was the inverse Fourier transform relationship. This is called the analysis or synthesis. Okay. And one of the things that is different is that this integral now is over any frequency of interval 2 pi, and is not from minus infinity to plus infinity, right? So that's one of the fundamental differences. The first property I'm going to talk about is also one of the fundamental differences, and implicitly we've done this in the examples that we've seen. So this is periodicity in frequency. And as we argued implicitly last time, there must be periodicity in the frequency because the unique frequencies in the discrete time only reside in an interval of 2 pi, right? From 0 to 2 pi. And after that, the frequencies wrap around. Or in other words, the exponentials of frequencies which are greater than 2 pi you're always going to be able to find another exponential which has a frequency between the interval 0 to 2 pi, right? So the unique is only between 0 and 2. So there's inherent periodicity. Now, what we can see is that inherent periodicity mathematically as well. And I can claim here, if I just look at the Fourier transform expression that you see up above, and I compute x of e raised by j omega plus 2 pi, right? And this is equal to, if I just plug this into the expression, what I get is n equals minus infinity plus infinity, x of n, and this is e raised to power minus j, and instead of omega, I have omega plus 2 pi times n. Okay, and if I just expand the exponential, right? So this is minus infinity to plus infinity. This is x of n e raised to power minus j omega n, and this is e raised to power minus j 2 pi n. Can I say something here about what this is going to be equal to? Anyone? So what is this e raised to power minus j 2 pi n equal to? Right, good. Right, so that's equal to 1, right? Because this is cosine 2 pi n plus sine 2 pi n. Cosine 2 pi n is always 1 because n is an integer, right? So this is indeed equal to 1. And as a result, this is n equals minus infinity plus infinity, x of n e raised to power minus j omega n. And this is the transform relationship that we had already, right? So this is like what I conclude now. I mean, through this rigorous evaluation, that the Fourier transform is now periodic, and that periodicity is in the frequency domain, right? So that's important here. The periodicity is in the frequency domain. That means is if I plot the Fourier transform as a function of the frequency, that will repeat itself after 2 pi radians per sample, right? As examples for this, I can quickly cite for you one of the examples we did. For example, we did x of n, small x of n, sorry, x of n equals a raised to power n u of n, where this absolute of a was less than 1. And we found out that this, for the Fourier transform for this, was equal to x of e raised to power j omega equals 1 upon 1 minus a e raised to power minus j omega, right? And clearly, I mean, is this periodic or is this not periodic? I mean, if I just look at the expression on the right-hand side, is this periodic in omega? And the answer is, of course, yes, because this thing here is actually periodic in omega. And the period is 2 pi. Clearly, it is periodic. And we actually saw this when I plotted this out as well. Okay, if you were to plot this out as a function of omega, and this was x of e raised by j omega, or the actually absolute value, right? So what we had was something like this, right? Or a rough sketch of this, right? And this was 0, and this was 2 pi. So it periodically repeated itself after 2 pi. So this is what we did last time as well, right? It was indeed periodic, right? Let me do another exercise here, which was KD, if x of n was equal to 1 for all values of n which were less than capital N and 0 otherwise, we found that the Fourier transform for this was equal to x of e raised by j omega is equal to sine omega n plus half. And this, I think this is what we did right towards the end of the class, sine omega by 2. And I can see it on the right-hand side pay, is this periodic in omega? And sine is periodic, yes, it is periodic. Sine omega by 2 is periodic. There's periodicity there, and that's why it's called the periodic sink, because it periodically repeats itself, right? Now, if I just look at the right-hand side, what do you think the period should be? Because I mean, when I look at it for the first time, this is the right-hand side. I mean, I'm just trying to verify कि यार ऊपर जो सब कुछ किया है, वो सही किया या नहीं किया, right? And I'm just given this expression here, and I want to figure out, is this expression correct? And one of the ways to see if this is correct is to check whether this is periodic with a period of 2 pi, right? But थोड़ी सी अगर inspection करूं मैं, तो I see कि जी ये जो चीज है, this is actually not periodic with a period of 2 pi, but rather periodic with a period of 4 pi. Is that not so? Right? Because this is omega by 2, right? So this must be periodic with a period of 4 pi. It cannot be periodic with a period of 2 pi. It turns out that the numerator and the denominator in conjunction are going to have a role to play. And I can check that if that is true or not, right? So I compute what x of e raised to power j omega plus 2 pi is, and this is sine omega plus 2 pi times n plus half divided by sine omega plus 2 pi divided by 2. And what do you get here? I can expand this out a little bit, and this is sine times omega n plus half plus 2 pi n plus 2 pi divided by 2, right? So this is what I get in the numerator. And what I have in the denominator is sine omega by 2 plus 2 pi divided by 2, right? So can I say that this is actually equal to sine? So let me use the entire screen here. So can I say this is sine omega n plus half plus pi, and this is sine omega plus pi. Can I say this is true? क्या ख्याल है? I mean, why did I get rid of that 2 pi n? क्यों अब्दुल्ला?
So that would be equivalent to like 0.
हाँ, equivalent to 0 क्यों? Because sine is
क्योंकि periodic था.
periodic, उसके अंदर मैं 2 pi multiples कोई भी डालूं, it doesn't make a difference, right? So, and because the key reason is capital N is an integer. Capital N is an integer, so that goes away, right? But can I simplify this a little bit further? The numerator divided by the denominator. I mean, plus pi करने से what happens to a sine or cosine for that matter? What is sine theta plus pi? Abdullah, does not become cosine. Cosine becomes when you add 90-degree. Negative. Excellent, Umar, right? So it becomes the negative of sine theta plus pi is actually minus sine of theta, right? So this is sine minus sine omega n plus half. And the similar thing I can say in the denominator as well. So this is minus sine omega by 2. And this minus cancels with the minus up above. And of course, then I see that this is indeed equal to x of e raised by j omega, right? So this is just a sanity check, if you will, right? Just a sanity check. Okay, the expression that I evaluated, is that periodic with a period of 2 pi? And turns out, yes, it is. And you can verify from the expression that I, or the curve that I drew, I mean, that was indeed periodic. I can quickly do a sketch here, right? So this is what is this periodic sink looks like. And then it goes up. And then goes up. And this is 0, and this is 2 pi, and this particular intercept is pi. And this corresponds to the case, by the way, for n equals 2, right? And this is 2 pi by 5, and this is 4 pi by 5, and so on and so forth, right? And you can use MATLAB to plot this out as well, and see, you'll see this all turns out to be periodic, and is this shape, and this is a sink pulse, and it's called a periodic sink. Okay, so this was the first property. Any questions about this before I go to the next property? All right, so this is property number 2, which is time and frequency shifting. So what do you mean by that? I mean, very, very similar to what we did in the continuous time case. The question is, if x of n has a discrete time Fourier transform given as x of e raised by j omega, the question is, what is the Fourier transform of n minus n naught? So, kya khayal hai? Any wild guesses or any educated guesses? Any educated guess on what this could be? Right? Thank you, Tala. Right? So you multiply by e raised to power says minus j omega, or a phase shift, as Ibrahim says, but the phase shift is not constant. The phase shift is a linear phase shift, right? So this is e raised to power minus j omega n naught times x of e raised to power j omega. And I am not going to do a proof for this. The proof is really, really simple. I mean, given that you're familiar with the proof for continuous time Fourier transform, but I would still urge you to try to do this on your own. Okay. Now, the next question is, okay, what happens if I do the shifting in the frequency domain? What happens here? So, Abdullah, is that nothing from before, or is there an answer to this? Okay, time domain mein kya hoga? So if you have a shifting in the frequency domain, what do you think would happen in the time domain? Or what operation in the time domain would correspond to a shift in the frequency domain? And this is very, very similar to what we did in the continuous time case as well, right? And or you would say, let's apply duality. So Talha, multiplying by n is sort of related to the derivative, right? So the duality sort of a thing is going to kick in. Okay, so let me do the proof here then, right? So I'd say, let me say y of n is the inverse Fourier transform of this new thing here, minus omega naught times e raised to power j omega n times d omega. I want to somehow transform the right-hand side into something which is a function of x of e raised by j omega. But in order to bring this into a form which looks like x of e raised by j omega, I see that this is not what I wanted. So I need to omega minus omega naught ko kuch aur karna padega mujhe. And what do? I make a change of variables, right? So, and that change of variables, excellent, Tala, change of variables, and let me use omega equals or v equals omega minus omega naught, right? And if I make that change of variables, it turns out that the y of n turns out to be equal to 1 upon 2 pi, and the integral which was over a 2 pi still remains over a period of 2 pi, and this is x of e raised by j v, and this is e raised by j, and this is v plus omega naught times n times d omega. And what happens here? This becomes equal to 1 upon 2 pi times this integral x of e raised by j v, and this is e raised to power j v n times, sorry, this is dv, this is dv, and this e raised to power j omega naught n comes outside because that's not a function of omega anymore, right? So that's a constant, right? And what I have inside this pink bracket is actually x of e raised by j omega, right? And consequently, what I have inside the pink brackets is actually x of n, right? So consequently, what I can say is that y of n is equal to x of n times e raised by j omega naught n, and indeed it's a duality here, right? So you shifting in the time domain is multiplication with an exponential in the frequency domain, and shifting in the frequency domain should be multiplication with an exponential in the time domain, right? Because of that inherent duality that we're sort of familiar with, right? So the answer to this here, let me fill the blank in here, and this is x of n times e raised to power j omega naught n, right? So let's see an implication for this, in particular the frequency shifting property. Ajitala.
So would this be raised by j omega n or n naught?
No, this is n, because the shifting is not by n naught. They can't, यहाँ पे, I mean, when I'm talking about this expression, when I'm talking about this expression here, I mean, there was no n naught anywhere, was it?
Yeah.
Right? It was just omega naught.
Okay.
All right.
Okay.
Now, let's do this example, which is, okay, let's say, okay, there was some signal whose Fourier transform you were given. And so this is x or h, let me call this h of e raised by j omega. And it's in the frequency domain is this box, right? Where this is omega naught and this is minus omega naught, or let's see, omega c keh dete hain. This is pi and this is 2 pi. And 2 pi, of course, you have a periodic copy, and this is minus 2 pi, you have a periodic copy here as well, right? And the height for all of the Fourier transform is 1. And I say, okay, this function is a or low pass signal. So that's why I use this LP in the subscript. Why do I say this is low pass? I mean, why is it called low pass? Right, because high frequencies are around pi. Excellent, right? So high frequencies are around pi, and the low frequencies around 0 and 2 pi. Right? Because 2 pi is exactly the same frequency as 0. Okay? So if this is the low pass signal, and let me just arbitrarily define another signal. और मैं कहता हूं कि यार इस low pass को I need to convert it into a high pass equivalent in the Fourier domain. So what kind of an operation would you imagine? Okay, is this low pass has to be converted to a high pass, and that operation will be shifting. Shifting by how much? Right, the shifting by pi. But Umar, I mean, the shifting is not going to be pi in the time domain. The shifting is going to be pi by pi radians in the frequency domain, right? So if this was pi, all I want is, okay, this to be shifted here, everything to be shifted by pi radians, so that the resultant thing that I'm going to get is something which looks like this. This is pi plus omega c, and this is pi minus omega c, or 0 के ऊपर कुछ भी नहीं है. And 2 pi, there's nothing here at 2 pi. What about 3 pi? 3 pi is where the Fourier transform is going to be non-zero. Similarly, at minus pi, the Fourier transform is going to be non-zero, and so on and so forth, right? And let me call this is the high pass equivalent, right? And where the relationship between the two is what the high pass equivalent is equal to the low pass equivalent, or low pass signal shifted by pi radians in the frequency domain, right? Now the question is, okay, this shifting operation by pi radians, what is it equivalent to in the time domain? What operation do I need to perform in the time domain to make a low frequency signal into a high frequency signal, right? And from here, I use the shifting property, right? So shifting property states what? That if I take the inverse Fourier transform on both sides, I take the x high pass signal जो है, right? If this is the inverse Fourier transform, right? And if I take the inverse Fourier transform here, what do I get here? I get x of low pass times e raised to power j pi times n, right? Where omega naught is actually equal to pi, right? E raised to power j. Abdullah, why an omega here? So the multiplication is going to be in the time domain. So if I just go back to, or let me write this here. I did the property here. The property is what? The property just says, okay, x of n times e raised to power j omega naught n. The Fourier transform for this is x of e raised to power j omega minus pi, omega minus omega naught. Right? So in other words, my omega naught in this particular case here is pi. Okay, so in the time domain, I just need to multiply it with e raised by j omega naught n, and omega naught is pi, so it's e raised by j pi n, right? And since the two are equivalent in the frequency domain, they must be equivalent to in the time domain as well. And what is e raised by j pi n? I mean, can I simplify that further? So this like X high pass signal is just equal to the low pass signal multiplied by -1 raised to power n. Excellent over, right? So it alternates between +1 and minus. So this is -1 raised to power n. So if I were to just shift the any discrete time signal in the frequency domain from low pass to high pass, all I need to do is I just need to multiply with -1 raised to power n, and that will make a low frequency signal into a high frequency signal. Okay? A low pass signal into a high pass signal, right? But what if I wanted to change a high pass signal back into a low pass signal? Excellent, Abdullah. So you took my words out of my mouth into the chat box, and vice versa too, right? So if I wanted to change a high frequency signal back into a low pass signal, that would still be a shifting of pi radians, except that the shifting is going to be in the minus pi direction. Okay? But minus pi direction shifting and plus pi shifting is exactly the same, because everything is modular, right? So plus pi radians is plus 180 degrees, minus pi radians is minus 180 degrees, but both of them are the same. Plus 180 is exactly the same as minus 180, right? Or in other words, e is by plus j pi n is exactly the same as e is by minus j pi n, right? So the bottom line is, if you want to convert a high frequency signal into a low frequency signal, even then you would multiply with a -1 raised to power n. And if you want to convert a low frequency signal to a high frequency signal, you would multiply with -1 raised to power n. Okay? And Abdullah, this is related to that comment that you made when we were talking about a raised to power n u of n. Do you remember? क्या हमने बात की थी?
I guess yes.
Right? So when we say कि a is positive, तो उसकी peak 0 पे आ रही थी. Right? And when a was negative, तो peak pi पे आ रही थी. Right? So this actually what was related, both of them were related to each other through a multiplication with -1 raised to power n, right? And that's a hint that I can give you. Try to create that relationship. Now, going back to example, the first example we did last time. Okay. Okay. The next property is that of conjugation. So, Ji Tala, go ahead.
Signal work in real life in a machine. अगर हम कोई signal produce कर रहे हैं, how is it? Like उसको क्या change exactly हम कर रहे होते हैं?
क्या कर रहे
If we are multiplying with -1 raised to power n,
Yeah.
so how is it like in a machine? How is that going to work if we are generating a signal?
So we're multiplying with -1. You see, discrete time signals कहाँ पे होते हैं हमारे पास, right? So discrete time signals, I mean, how do we operate with discrete time signals? How do we compute discrete time signals, or how do we जो है implement operations on discrete time signals? क्या ख्याल है, तला?
I was having a trouble with this. How are we going to do that?
In a computer.
Yeah, but what would it mean? -1 raised to power n जब multiply कर रहे हैं with the signal. What would it mean in a if a computer is generating a signal?
Yeah.
And so a time shift would just mean कि वो आगे या पीछे हो जाएगा.
In the frequency domain आगे पीछे रहेगा. So let me give you some sense here. Let's say you get a signal which is recorded audio, right? And when you record that audio, you get access to it in the form of an array. If you use MATLAB to record your audio, I mean, this is going to give you an array. ठीक है, एक array होगा, एक पूरा का पूरा vector होगा जिसके अंदर सारे के सारे elements पड़े होंगे, right? And this is a discrete time signal. And if this discrete time signal, you wanted to say that you wanted to shift the pitch of this signal, right? What do you mean by pitch? कि मैं अपनी आवाज को थोड़ा सा और डल करने के बजाय थोड़ा सा और मैं वो करना चाहता हूँ, right? Shrill करना चाहता हूँ, right? So I want to increase the pitch. And if increasing the pitch basically means what? You take the Fourier transform and shift the Fourier transform in the Fourier domain, in the frequency domain. Okay? So I say, yeah, why don't I just do this? Okay, n equals 1 length. So this is MATLAB code. Length of x, and x high pass, I'd say -1 dot raised to power n dot steric x. And this would give you a signature. Let me use y here.
ठीक है, this would give the signal. ठीक है.
And when you play y, although there are problems with this, I mean पाई के शिफ्ट से ऑडियो के साथ पता नहीं क्या कुछ और हो जाएगा, कुछ आपको आवाज ही नहीं आएगी मोस्ट लाइकली, राइट? बट लेट्स से यू से कि जी मैंने शिफ्ट जो है थोड़ा करना है, लेट्स से पाई बाय 8 का करना है, राइट? सो देन देयर आर थिंग्स यू कुड डू, व्हिच इज e raised to power j pi by 2 pi by 8n, and that would just slightly shift it and not too much. Okay. I actually put up some there's material available on LMS for this. So EE100 की labs हैं, उसमें I did my own audio, and I think the audio is there शायद.
हाँ, audio बात I was just having trouble imagining कि ये data store किस तरह होता है. And data नहीं
करते हैं, data store जो arrays में होता है.
हाँ, ठीक है.
Yeah. But and by the way, I mean all of you are taking microcontrollers class, right?
DCC microcontrollers.
Okay, microcontrollers बाद में आना है. So microcontrollers, if you DLC is just a baby version of microcontrollers. Okay, so you would use a microprocessor, and that microprocessor would take in data from the real world, so through some sensing, right? And that was always stored in an array inside a microprocessor, and then you do operations on it through programming, right? And by the way, so thank you for bringing this up, Talha. And why is discrete time signals so important, right? If you recall, if you go back to the beginning, I said, very beginning, I said that there are many signals which are inherently discrete. And for example, this COVID data that we have, I mean, it comes in every day. But then there are many, many other signals that are inherently continuous, but we discretize them through sampling or through ADCs, analog digit conversion. And after that sampling, we get a discrete time signal, right? And once we have that discrete time signal, all of the processing we do is actually in the discrete time domain and not in the analog or the continuous time domain. So आपके जितने भी, I mean, this computer you're hearing my audio through a digital system, and all of the processing that's being done on my audio in it going from my laptop here to your laptop or to your phone at your places, right? All of this is actually a discrete time signal, right? The discretized होता है, computer में जाता है, it is processed in the discrete time domain through some algorithms, and then goes up to you, and then is played to you in the continuous time domain. Okay, so the reason why it's become so popular is because of this digital age, right? So everything is digital, all the data is digital, all the signals are digital, and therefore all of the processing has to be digital as well, right? And that's why it's so important to study discrete time signals. And that's why there's a separate course which is called digital signal processing, which comes after signal. That's an elective course. Okay?
Yes, sir.
All right. Achha, so the third property I want to talk about is time reversal. And I'm just going to gloss over this because you should be able to derive this on your own. So if I flip the discrete time signal in the time domain, what happens in the Fourier domain? तला क्या होता है? या चले कोई और बताएगा? और कोई मैं सीपी मार्क कर दूं यार किसी की? Right. So it's flipped as well, right? In the Fourier domain, it's flipped as well. Good. Okay. So unmute करने के 5 points हैं, chat में बोलने के 2 points हैं सिर्फ, as I told earlier as well, right? Right. So this is x of e raised by minus omega. So if you flip the time domain, the Fourier domain is flipped as well, right? Now I'm going to come to this conjugation. and conjugate symmetry, right? And this is I mean, a consistent theme that we've seen across, I mean, Fourier series first, and then Fourier transform, and continuous Fourier transform, and now discrete time Fourier transform. So the question is, and so that's why I'm not going to do the proof for this, explicit proof for this. The question is, if I take the conjugation in the time domain, what happens in the Fourier domain? Right, excellent, Abdullah. Right, so this is what happens is there's a conjugation in the Fourier domain and there's a flipping. So there are two operations. So conjugation in the time domain results in a conjugation and a frequency flipping in the Fourier domain, right? And you can go ahead and prove this. It's quite easy, right? I wanna quickly go over Kiji. If x of n is real, so what can I say about x of e raised by j omega? The usual stuff, right? Which is x of e raised by j omega is equal to x conjugate of e raised to power minus j omega, right? It's exactly what we did in two of the modules, right? So this is called conjugate symmetric. Similarly, if I say Kiji, if x of n is real and even, what can I say then? Then x of e raised by j omega, कौन बताएगा जी? This is halwa points. If x of n is real and even, what can I say about Fourier domain? वो क्या होगा? Hamza?
X conjugate of E of j omega.
X conjugate of e raised by j omega, which basically means what? That the Fourier transform is real, and so on and so forth. I mean, so what if x of n is real and or the Fourier transform is purely imaginary, right? And so on and so forth. Right? So similar things that we've done earlier, right? I wanted to address this क्योंकि this was part of the exam and जिसमें सिर्फ एक स्टूडेंट ने इसको सही किया. So let me say, चलें, this is exercise. So, and the question is, okay, if x of e raised by j omega has a Fourier inverse of x of n, what is the Fourier inverse of the imaginary part of x of e raised by j omega? And here, and the results are exactly the same as those that apply to continuous time Fourier transform. But I want to go through this nevertheless, because what I saw people doing was they just looked up some formula or relationship in a table and just applied it, right? And there's only one student who did it perfectly, right? And वो टेबल में क्या लिखा हुआ है? टेबल में सबने ये लिखा हुआ है कि j times imaginary of x of e raised by j omega is equal to has a Fourier transform of odd of x of t. But I don't really like to remember this kind of stuff, right? I just know the fundamentals, and using the fundamentals, I can do anything, right? So here's what I would do. So the first thing is, what is imaginary of x of e raised by j omega? इसका मतलब क्या है? If you want to extract the imaginary part out of a complex number, how do you do that? So if you want to extract a real part of a complex number, what do? You say real number whatever the complex number was plus its conjugate and divide by 2. I mean, that would make sure that the imaginary parts cancel out and the real parts are left, and then you divide by 2 because you're just adding, right? And that will give you the real part. What if you want to extract the imaginary part? वो किस तरह निकालते हैं किसी complex number का? And this is x of e raised by j omega minus x conjugate of e raised by j omega. And if I do the subtraction, what am I going to get at the end? If I subtract the conjugate of a complex number from the complex number, the real parts cancel ho jayenge, right? The real parts are going to cancel. What about the
Yes, sir.
imaginary parts?
So that will be minus 2 times.
Minus 2 plus 2 times.
Oh yes, plus 2 times.
Right? So इसमें चलें. Let me say कि ये है अगर, right? So if I just, so this is equal to, I claim that this is 2 times j times imaginary part of x of e raised by j omega. This is what you get. And then you need to divide by 2j. Excellent, right? So this is how I would just, so imaginary of x of e raised by j omega is actually equal to 1 upon 2j x of e raised by j omega minus x conjugate of e raised by j omega. And then you say, what is the inverse Fourier transform of this imaginary of x of e raised by j omega? So this is 1 upon 2j Fourier inverse of x of e raised by j omega minus Fourier inverse of x conjugate of e raised by j omega. And this is outside. And this is equal to 1 upon 2j. And this is x of n. और ये यहाँ पे क्या होगा? So what is the Fourier inverse of x conjugate of e raised by j omega? So it turns out this is x conjugate of minus n. Right, so this is how I would go about this. And then I claim that if x of n was real, if somebody were to tell me that x of n was real, then I'd say if x of n is real, the x conjugate of n is equal to x of n. And that's why, so if xn was real, then the Fourier inverse of imaginary of x of e raised by j omega is equal to 1 upon 2j times x of n minus x of minus n. And that's it. Okay, so I'll start from the fundamentals. So always start from the fundamentals. Okay, and they will not lead you astray. All right. Any questions before I go to the next property? Okay. So this is property number 4, which is difference and accumulation. So in continuous time, the analogous of continuous time differentiation in the discrete time is called the first difference. Which is first difference क्या है? That is just x of n minus x of n minus 1, right? So this is determining the change. So if you're given a discrete time signal and you're asked to determine the first difference, so that essentially when it computes the change in adjacent signals, right, or adjacent samples. So in other words, अगर आपको मैं COVID data दे दूं, right? So this is I give you the total number of cases, right, reported on each day, and then you compute the first difference. The first difference will tell you, okay, what was the increase, or for that matter, decrease on any given day compared to the previous one, right? And that's called the first difference, and that's extremely important, extremely in many applications. In the Fourier domain, what happens is, if you take the first difference, what do you think kya hoga? So we have enough information, or we have discussed enough properties so far to be able to derive what x of n minus x of n minus 1 will be in the Fourier domain. What do you think? Yeah, Ji Talha?
So shifting होगी और उसको minus वो 1 हो जाएगा x of n multiplied by e raised to power j e raised to power j omega n.
Yeah, so this is okay. So one property that I've not explicitly done here, maybe should have, which is linearity, right? Okay, linearity says that the Fourier of x of n minus x of n minus 1 is actually equal to the Fourier of x of n minus the Fourier of x of n minus 1.
Yeah, मैं वही कह रहा था.
Right? And the Fourier transform of x of n is, I know, is x of e raised by j omega. And the Fourier transform of x of n minus 1 is, you go to that time shifting property where this n naught is actually equal to 1, right? And this is e raised to power minus j omega times n naught, but n naught is 1, and so that's there. And this is x of e raised by j omega. Right, so essentially what this therefore is 1 minus e raised to power minus j omega times x of e raised by j omega. Okay, this is what happens when you compute the first difference. Now, what about accumulation? So this is called first difference. This is called first difference. What about accumulation? And what I mean by accumulation is summation from k equals minus infinity all the way up to n x of k. Right? So basically past में जितना कुछ हुआ था, right, उस सबको add करके all the way up to n मुझे बता दो. In other words, if you go back to that COVID data, if you had the daily confirmed number of cases per day, and I asked you, what is the accumulated number of cases, right, up until, for example, April 23rd, 2021, right? And up until the 22nd April 2021, or up until 21st April 2021. So from that daily confirmed number of cases, all you will do is you just compute this accumulation, right? Or accumulation operation. You say y of n is equal to this. Summation from k equals minus infinity, right? So the accumulated value evaluated at any time instance n is actually equal to the summation of x over all values from the past summed up until that particular present day, which is n. Okay? And it turns out that this accumulation is the inverse operation of difference. Right? Is that clear? You should be clear as well. कि अगर मेरे पास accumulated values दी हुई है और मैं उस accumulated value के ऊपर difference दे देता हूँ तो मुझे वो पुरानी चीज मिल जाएगी, right? So and I'm going to give you a proof, giving this result without a proof, right? So turns out that this is equal to the Fourier transform for this is 1 minus e raised to 1 minus j omega times x of e raised by j omega. That should be a little clear enough, क्योंकि accumulation is the inverse of first difference. So multiplying 1 with 1 minus e raised by minus j omega, there should be division by 1 minus e raised by minus j omega. Lekin because of reasons that we sort of discussed in the continuous time case as well, which I am not going to go into a lot of details, there is a separate term that is added, right, which is equal to pi times x of e raised by j 0 and summation. अच्छा, अगर मैं ये यहाँ पे कह दूँ कि this is delta of omega, would things be okay? I mean, or is there some error here that needs to be fixed? If you just look at the right-hand side expression, right? If you look at the right-hand side expression and see, is this a valid discrete time Fourier transform? And the answer is it's not a valid Fourier transform. Why is it not a valid Fourier transform? Abdullah, you think it's an error?
So if x was a function of omega, then it would have been fine, but it's a function of e raised to power j omega. So I think that's why.
Okay. Umar, you want to say something?
ये डेल्टा जो है वो उसको नॉन पीरियोडिक कर देगा, मतलब वो जीरो हो जाएगा सब.
Excellent. Excellent, right? So,
डेल्टा की ट्रेन चाहिए होगी.
Zabardast. So Abdullah, as far as this is concerned, I mean, this is a constant. I mean, that's what I meant by saying that this is x of e by j0. That means that this is the Fourier transform of x evaluated at omega equals 0. So this is some value, right? But the problem, as far as this expression is concerned, this delta of omega only resides at omega equals 0, right? But I know that the discrete time Fourier transform must be periodic. So there's no periodicity there left, right? So that means there's some error here. And indeed it is. Actually, ये value ये नहीं होती, right? So what you actually have is a train of impulses. And this is k going from minus infinity to plus infinity. And this is delta of omega minus 2 pi k. And what that means is there's a delta residing at omega equals 0, and then another one at omega equals 2 pi, another one 4 pi, plus minus 4 pi, plus minus 2 pi, plus minus 6 pi, plus minus 8 pi, and so on and so forth. Every multiples of 2 pi, spacing of 2 pi, you have the delta, and that's a periodic extension. Okay? So I know I have not gone about the proof for why this is so, right? So let's just take my word. I will let you take my word for it, right? As I'm going to provide this without a proof, right? But the things are very, very similar to what we had in the continuous time domain, right? In the continuous time Fourier transform, we had something very, very similar, right? Except कि वहाँ पे 1 upon j omega से division करते हैं. यहाँ पे we divide by 1 upon 1 minus e minus j omega, and you still have an impulse, but that impulse has a train of impulses because of the fact that the Fourier transform must be periodic. Okay. Now, let's just apply this formula, if you will. So I'm going to put this up here, right? So this is what I'm going to, and try to apply this relationship to the following, which is x of n, let's say x of n equals u of n. And you are required to find the Fourier transform of this unit step, right? Now, the Fourier transform for this does not converge. So this is something I should have mentioned here earlier as well. So x of n is not absolutely summable. What I mean by that is the following. That that summation n going from minus infinity to plus infinity, u of n, the absolute value for this is actually equal to infinity, right? So it's not absolutely summable. This means that if I sum the absolute value up, right, this diverges, right? So this goes to infinity, right? And we know that the Fourier transform, the DTFT, is known to converge if and only if x of n is absolutely summable. So the Fourier transform is known to converge if and only if the Fourier transform is fxn is absolutely summable, but u of n is not absolutely summable. But we can still determine the Fourier transform in terms of the delta function, as we're going to see. Okay? And as I'm going to argue, yeah, there's no inconsistency here, even though I'm going to specify the Fourier transform for the unit step. But the fact that it involves a delta function just drives home the point that the Fourier transform for u of n does not actually converge. So everything remains consistent. Now here's a question, KG, how do I use the differencing property or the accumulation property to determine the Fourier transform of the unit step? So Abdullah mentioned something about the derivative property. What do you mean by that?
सर वही फर्स्ट डिफरेंस लेके एक और सिग्नल डिफाइन कर लेते हैं और देन विल फाइंड फोरियर ट्रांसफॉर्म ऑफ दैट सिग्नल और फिर उसको कन्वर्ट कर लेंगे.
Okay, so I would so u of n के साथ कौन सा ऐसा सिग्नल है जो कि रिलेट होता है थ्रू द फर्स्ट डिफरेंस प्रॉपर्टी और थ्रू द फर्स्ट डिफरेंस?
सर डेल्टा.
Delta, excellent, right? So the first difference of the unit step is delta, right? So we know that u of n minus u of n minus 1, this is equal to the delta n function. And we also know that u of n is equal to the accumulation consequently, because the accumulation k going from minus infinity to n delta of k, right? So this is the first lecture of module 4, right? The second lecture of module 4, I think, right? So this is something we know. And here's, let me say, let g of n, so make my life a little bit easier. Let g of n be delta of n, right? So the question is, what is g of e raised by j omega? So g of e raised by j omega, I can apply the definition. This is n going from minus infinity to plus infinity. G of n e raised to power minus j omega n, and this is summation n equals minus infinity plus infinity. This is delta of n e raised to minus j omega n. So what is the sum equal to? What do you think? So Hamza, Rashid, what do you think?
I'm not sure, sir.
Right. So this comes about from the sampling property of the delta function, right? So we I think it was 2 lectures ago, right? And if I give you a rundown, it's the fact is, KG, this value here, or this function here, is non-zero only when n equals 0, and all other places are 0. Okay? So even though the summation has infinitely many terms, I mean the indexing, but only one of them is non-zero, and that corresponds to the term corresponding to n equals 0, right? And the non-zero term for delta of n is equal to 1 for n equals 0, and is equal to 0 for n is not equal to 0. Okay? So therefore, this would be equal to e raised to power minus j omega times 0, which is just equal to 1. Okay? The sampling property of the delta function, right? So the Fourier transform of the unit impulse is equal to 1. That's something we know. All right. Now, let me see if I can make some space. All right. So then, what is u of e raised by j omega? right? I can use this so given k, u of n is equal to summation k equals minus infinity to n g of k, right? If this is something I know, then all I need to do is to determine u of e raised by j omega is to apply the accumulation property, right? And what is that accumulation property? Accumulation property u of e raised by j omega is equal to 1 upon 1 minus e raised by minus j omega. So मैं क्या कर रहा हूँ? I'm just copying this thing out. I'm just copying this thing out, right? But instead of x, because there's no x here, there's g here. Instead of x, I'm just going to plug in capital G, and that's it, right? So this is g of e raised to power j omega plus pi times g of e raised to power j 0 times summation k going from minus infinity to plus infinity delta omega minus 2 pi k. And I have the result here, right? So this turns out to be equal to, therefore, this is 1 upon 1 minus e raised to minus j omega. G of e raised by j omega is 1. So therefore, this is pi and summation. And this is u of e raised by j omega. Right, so this is the Fourier transform of a unit step function in the discrete time domain. Okay. Let me put up some exercise here. Verify that 1 minus e raised to a minus j omega times u of e raised by j omega is equal to 1. Okay, so go ahead and verify that. All right, any questions here? So this is the result. Okay, so I won't have time, I think, to start the next property. What I can do instead is just another example. And so what you're given is, this is x of e raised by j omega, the absolute value of some Fourier transform. This is what it looks like. This is minus pi, and this is pi, and this is 0. And this is the phase plot. This is the phase of x of e raised by j omega. And what the phase looks like is the following. So this is pi, and this is minus pi. So this is just a straight line. And this is 2 pi, and this is minus 2 pi. Okay, so this is the Fourier transform given x of e raised by j omega and the phase of x by j omega so determine whether x of n is real or even. Okay, so let's do this. KG, सबसे पहले let's try to answer this. Is this real or not? Is the time domain signal real or not? Is there enough information available to us from these two graphs for us to be able to see okay, is the time domain signal real or is the time domain signal complex? What do you think? जी उमर,
वो मैग्नीट्यूड इवन है और फेज जो है वो ऑड है, तो उस वजह से हम कह सकते हैं कि वो रियल है।
time domain signal real है, right?
जी
Good. And why is that something you remember or?
सर ये सर्किट्स में इस तरह हमने किया हुआ है कि
Okay.
हमेशा मैग्नीट्यूड जो होता है वो इवन आता है और फेज ऑड आता है क्योंकि
Yeah.
रियल सर्किट्स होते हैं।
Yeah, but we've not yet talked about के phase or real imagining के साथ क्या ताल्लुक है. All we know is कि if x of n is real, then we know that x of e raised by j omega must be equal to x conjugate of e raised by minus j omega, right? So this is something we know, right? Right, and if this is something we know, from here I can show, yeah, this must imply that the magnitude is even and the phase is odd. असल में आता वो यहाँ से, right? And here's how. So if x of e raised by j omega is equal to the absolute value of x, right? And then there's the phase, right? Which is e raised by j, and then the phase. And what about x conjugate of e raised to minus j omega? Right? What happens there? That means that this is x of e raised by j omega, right? Conjugation say क्या होता है? Conjugation does not change the magnitude. All that changes is the phase, right? So this is e raised by minus j, the phase of x of e raised by minus j omega, right? And if this is 1 and this is 2, right? And if both of them are same, so you can just compare these two. If you compare the two, then I can conclude that x of e raised by j omega absolute value must be equal to the absolute value of x of e raised by minus j omega. Because if two complex numbers are same for all omega, that means their absolute values must be the same and their phases must be the same, right? And the second property is that the phase of x of e raised by minus j omega must be equal to the minus of the phase of x of plus e raised by minus j omega, right? And this means this is the magnitude is even, and this means the phase is odd, right? So if x of n is real, that must mean the magnitude of the Fourier transform must be even and the phase of the Fourier transform must be odd. And if I go back and look at the two curves that I'm given, as Umar pointed out, both of them indeed satisfy this condition. The magnitude is appears to be even, and the phase appears to be odd. That means okay. So since the given magnitude, given x of e raised by j omega is even, and the phase is odd, then that means x of n must be real. All right. The question is, okay, so that's the first question. The second question is x of n real? Is x of n real? What do you think about that? No, sorry, ये तो मैं answer कर दी. Sorry. Is x of n even? Is x of n even or odd? Or nothing? The answer to this, so nobody has an answer to this, is x of n even? If I just look at these two curves, right? So the magnitude curve and the phase curve. Can I say something about the evenness of x of n? Right, the answer is yes, I can. So x of n is not even. Because if it was even, the Fourier transform must have been even as well. And then clearly the Fourier transform is not even because the phase is odd. If the phase is odd, the Fourier transform cannot be even, right? And then the question is x of n odd? And the answer to this is no, it's not odd either. Right? Because if it was odd, both the phase and the magnitude should have been odd. But the phase is odd, but the magnitude is not. Right? So therefore it cannot be odd. So the function or the signal is, we find out, is a real signal, but that real signal is neither even nor odd. And therefore for the Fourier transform turns out to be complex, clearly. Okay. I can build on top of it though, right? So I can say कि क्या कहूँ मैं? Right. So let's say कि y of n is equal to x of n minus n naught. So is there an n naught which makes y of n real and even? Right, so this, I can leave this off as an exercise. Okay, so I'm going to stop here. Time's up. Any questions about what we've done?
So even के लिए condition बता दें दोबारा ग्राफ से देख के कैसे बताते हैं?
Right, so even के लिए, so let me here. Okay, if x of n was even, right, then x of e raised by j omega must be equal to x of e raised by minus j omega, right? This must imply that the magnitude is even and the phase is even. दोनों के दोनों even होने चाहिए, the magnitude as well as
Okay, so if both things are even, then the signal is even, and if both things are odd, then it is odd.
yes, true.
Okay.
यहाँ पे लेकिन magnitude even है लेकिन phase odd है, so both those conditions are not satisfied.
Okay.
ठीक है? Any other questions?
सर आपने एक्स ऑफ ईजे ओमेगा को कॉम्प्लेक्स कहा था, वो किस तरह कहा था?
किसको सॉरी?
ये एक्स ऑफ ईजे ओमेगा को,
Yeah, वो
द
इसलिए
ग्राफ इज क्लियरली कॉम्प्लेक्स।
yeah, the graph is clearly complex because it has a phase which is non-zero.
क्योंकि फेज इंट्रोड्यूस होता है कॉम्प्लेक्स पार्ट की वजह से।
Yeah, अगर वो फेज देखें, अगर फेज जीरो हो रहा है ना तो वो तो रियल एक्सेस पर सारी चीजें रिजाइड करेंगी,
ठीक है।
राइट? सो आई मीन इफ आई कैन सी, अगर ये चलें, ये रियल एक्सेस है और ये इमेजिनरी एक्सेस है, तो इफ आई जस्ट लुक एट द पोलर कोऑर्डिनेट्स, राइट, तो पोलर कोऑर्डिनेट्स में फॉर my vector to be residing on the real axis, my phase should either be 0 or it should be pi. ठीक है? That would mean कि वो the signal is real. But if the phase is non-zero, इसका मतलब वो कहीं यहाँ पे reside करता है या फिर किसी और पूरे plane में reside करता है कहीं पे, right? And clearly this phase is not zero. This phase is not zero. Is that clear, Umar?
यस सर।
ठीक है. Right. Any other question?
एंड पे जो आपने नीचे कर दे,
नीचे?
बिल्कुल एंड पे आपने लाइन लिखी थी, आई जस्ट नीड टू सी।
Yeah.
कर करते हैं। थैंक यू।
ठीक है.